Okay, so welcome back. Uh, so in this particular session, I will talk about the developing efficient ML accelerators and then how LLM can help there. Okay. So, in the context of the course, this ML is something is being used, right. So, you kind of create some machine learning model for say some cyber security attack detections and all, and then you want to put it into that edge devices and all, right, and that is what is called accelerator, right. So, it basically try to execute it on some hardware and you want to create a application specific hardware in the sense that it only execute that particular trained model, right. So, here as I mentioned, it is not on the training part, it is basically once you have trained model on some data sets and all, that model I want to run there to infer something, right, for classification or all the other machine learning tasks. So, basically it is some for inference. Okay. So, that is something we will talk about, and so in now I will basically to talk more detail on high level synthesis, right. So, in the first half I talked about that once I use high level synthesis, the conventional high level synthesis for developing secure cryptographic implementations, we found that they are not good enough, right. They do too much of modifications and that is counterproductive, right. But in the context of this ML accelerator design, that high level synthesis has huge role, I would say, because you think about that a trained model, what is that? It is basically a Python code, right. It has certain, as Professor Mishra was mentioning, it is basically kind of a deep learning model. You have lot of neurons, there are multiple layers and each layer there are lot of neurons and they are connected to each other, right. And it was something Wi into Xi, some that multiplication is happening there, the weights and biases. So, that is a Python code, right. And hardware implementation means you need a hardware this Verilog implementation or VHDL implementation in register transfer level design. So, what is the choice you have? One is the same way that you see that code and you write your design, that is too time consuming, right. In this fast world, everybody want to press for time, they want to develop this design as soon as possible, right. So, developing those Verilog or the RTL design directly for this your architecture is time consuming and it is not something a viable approach. On the other hand, this high level synthesis is exactly for designed for this purpose, right. You have your model in Python, C, C++, and it can automatically convert these things into hardware in RTL. So, why you should not use the RTL, I mean high level synthesis here, and I do not need to make any security guarantee here, right. I want to make an efficient implementation, and this tools has lot of such features that will help in developing efficient hardware from higher level behavior. So, for developing this ML accelerator, high level synthesis is a good fit. Okay. So, we should utilize this high level synthesis in this process, understood. So, then we should know what is high level synthesis in a nutshell, right. So, I think the term high level synthesis is not maybe familiar with you if you are not working in this domain. So, what I will do at the start, I will just give a brief maybe 5 minutes, 7 minutes overview of high level synthesis, what it happened internally, right, what this tool does essentially to convert a C code into RTL code, right, register transfer level design. And then we will identify where actually what is the kind of difficulty in using this high level synthesis in developing machine learning accelerator, and we will identify those limitations or the difficulties or manual involvement. And nowadays LLM is being used to make many mechanical job automate, right. It basically can be used to automate many mechanical tasks, right. So, we will basically see how LLM can help in this high level synthesis process, whatever the manual involvement there, how can LLM help in this process and make that process faster, right. So, that your overall time to design a ML accelerator is reduced. Okay. And then we will talk about this how do you actually do this process with LLM plus HLS, and then some results and future tricks. Okay. Any questions so far? Okay. So, this I think I do not need to give more emphasis that nowadays deep learning algorithms inference is happening on edge or IoT devices. It is something well known, right. So, I think we are all convinced at this point, and I do not want to give more focus on that, why we should do that. And there are some recent work which I just connected here, which basically targeting either for ASIC or FPGA targets, right. So, this there are a lot of already effort. It is not that I am the first person talking about this, right. If you open this domain, there are a lot of research, people try to do many ways. Okay. So, what do you mean by this hardware acceleration? So, when you try to put this, so this figure is actually important for you. Once you try to have a this model which is trained, if you try to put it into hardware, and if your what you try to do there, you try to make it lightweight, right. So, you all talk about that, I do not want to make a very high overhead or high latency design, right. So, there are many ways I try to minimize the size, and sir was saying that the one option is that you identify some of the nodes which is not so important and remove them. So, size of the model will reduce, right. That is one way of approach. The other very important approach is basically this quantization, right. So, this quantization is basically it talks about that your actual weights, right, may be 32 bits. What about using 8-bit version of that, right. So, that means straightway your size will be 4x less, right. So, that is the one idea that you try to quantize to 8-bit or 16-bit or 4-bit, whatever is needed, without much compromising the accuracy. So, actual accuracy may be 99%, it become 98%, 97%, which is okay type, right, but area overhead become 1/4, right. So, that is one approach, and the model pruning is the other thing what Professor Mishra was talking about, that you try to discard the nodes or the weights, that is not so important. Okay. So, this is being done, and say somebody has already done that, and you have given that version of the code, right, before high level synthesis. So, what I will do, as I mentioned, that I will talk about high level synthesis in more detail. I mean, what is, it is not a magic, right, it is basically a algorithmic steps through which you can convert a C++ behavior into register transfer level behavior. Okay. And the advantage I have already talked about, the shortened design cycles, that it will reduce the time, because if you write your Verilog code, it will take lot of time, and it is just a minute, right, within minutes you can get this in. This is another very important advantage of this high level synthesis, which is called design space exploration, is from the same specification I can develop a design which has less power, I can develop another design which has less latency, I can develop another design which has area latency trade off and have a balanced version of that. All those is possible, and that is called design space exploration, right. With high level synthesis, just changing few parameters you can do that. So, from the same C++ model, I can create a RTL which is very low power, I can create another design within few minutes which has very less area, and so on, which is almost double effort when you try to do directly in RTL, because I develop something low power, that version I cannot tweak and make latency intensive, right. So, you have to start from fresh, which is not needed in high level synthesis. Okay. And it has lot of such optimization, you have to just use them to do this, right. So, this is the advantage. The steps there in high level synthesis is, first is compilation. I will not give in much detail, but I think it is a good idea to see what happening inside in this box of high level synthesis. It has allocation, binding, scheduling, and then data path and controller generation, and it will give you the RTL. Okay. So, I will just walk through an example with some diagrams to show you that what happened internally. So, C version, so the Python and C, I can convert a Python code into C code, right. So, there are converters. So, you can think about that, I have a C version of the model with you. Okay. So, how a C program runs? If I give a 10 line of codes, how it happens? The first line execute, then the second line, then third line, and so on, right. It is kind of a top down, right, sequential execution. But in the hardware, if you have two say adder in your design, what will happen? So, suppose you have two adder, some data is coming here and it is going somewhere. So, if there are two adders, in every clock you can do two operations, right. Basically, hardware is inherently parallel, right, whereas your C++ code is inherently sequential, So, the model of execution of hardware versus software is different, right. So, the way your C code execute in your processor also that sequential nature. So, that is a fundamental difference. And the second thing is a timed behavior that as I discussed in the first half also, that whenever you have given in something, you have to tell what exactly happening in clock 1, then in what exactly happening in clock 2 and so on, right. This is basically time. I can tell that in time clock this will only happen in this design, nothing else will happen and so on. Whereas, in C there is no concept of time, it is an untimed behavior, it is just top down execution, right. So, it is not very trivial to convert a C code into RTL. It is basically functionally equivalent, but their model of execution is different, their timing behavior is different, but still they both perform the same thing. If you give the input to this C code, whatever output will get, you give the same input to this RTL design, that will give you the same output, right. That is the kind of objective, but this transformation, unlike whatever you discussed in the first half, it is not trivial, right. Lot of decision making is happening inside, and I will just walk through you through this process. Okay. Just to give you some feeling that how it looks like. So, you basically have a C code like this, where you have a while loop, set of statements and then it is happening in the loop and all. Whereas, if you see a Verilog code, just I took it because if you take this code and if you convert it into Verilog, there may be 100 line of code. So, I just took some of them. We are saying that if this process of clock, if this you are in this state, then you update only this register, right. If you are in this state, then you do this, you just reset this register and so on, right. This is the wire transfer, this is the conventional operations. Here you are saying that if this is the state 2 and if your this condition is hold, then you go to state 1, otherwise you go to state 3. So, this is how your Verilog will look like, right. This is does not have any correlation with this apparently, but these are they are the same thing, right. So, how can I convert this into that? That is the question, and that high level synthesis does very efficiently. Okay. So, what I will do is, so basically your RTL will look like this. You have a data path where you have set of function units, set of registers, they are connected, the output is going back to registers. And why, by the way, this is called register transfer level, and can anybody tell me why this name of this design is register transfer level design? Can anybody explain me? Any idea? Because what is happening here, in every clock, value of registers coming to this function unit, operation is done, go back to register, right. So, the transfer of value from register to register, right. That is why this is register transfer level behavior. So, I am explaining everything in terms of how your registers getting updated in every clock in terms of input and the register values. Understood? So, effectively if you have this code, this will convert into this, and structurally you will have a data path that will execute these operations, and there will be a controller that will effectively control these operations. And the first important thing is that you cannot do everything in one clock, right. You have to do in multiple clocks. So, that is the first decision. You have decided, say that I need 4 clocks, say, to execute this. So, based on that, it will say that clock 1 it sets some signals to this, so that a specific set of operation will execute here. Clock 2, suppose you decided that I will do this part in clock 1, this part in clock 2, this part in clock 3, this part in clock 4, and this is in clock 5. Accordingly, it will send the signal, so that same data path can execute this in clock 1, this in clock 2 and so on, right. So, this is how the overall structure of your design. Okay. So, I will just quickly go through what are the steps, how do you basically do that. So, as I mentioned that you have this behavior, you cannot execute, the first decision is that you cannot execute everything in one clock, then your circuit will be not feasible. So, the first decision is that you figure it out the basic structure of your design. So, it is basically say that CDFG, control and data flow graph, what is how the control flows among this behavior. So, this is basically your B1, right, and then once it is done, then you probably do the output Y, that is your B2, and this reading part is basically B1, right. So, this is the control flow, right. So, this is the while loop, when it is done, then it will go to B2, right. and then within this among this operation what you do, you identify what is the data dependency among them, right. So, you break this bigger expression into smaller expression. So, this bigger expression you do not know how to execute. So, what I do, I break this into smaller expression. What I did, I just say that this value I will store in T1, I will take this value I will store in T2, I will take 3 this 3 into y I will store in T3, and then u into dx into T4 and so on, right. This is how I break the entire behavior into smaller code. So, that I can tell that you do this part of the code in clock 1, this part in clock 2, this part in clock 3 and so on, right. So, that is actually help you to, if you break the bigger expression into smaller 3 address code, then you can tell which operation is going to happen in which clock, right. So, this is what happened inside the tool. So, tool actually does that, right, and then it identify the dependency. This is the dependency. What is the dependency? Why the dependency is coming? So, you see this is you are doing this T1 equal to this, and here you are using T1, right. So, until, so this value is coming here, right. So, you are doing this this is T1 and that value is coming here to calculate T5. So, that means until this operation is being done, you cannot execute this operation, right, because there is a dependency from this one, and similarly from this operation also there is a dependency to this, and this is exactly showing that, right. For this operation, this is your T1, this is your T2, and they are coming here, right. So, this dependency, why it is important? It says that in which order you should does this operation, right. I cannot execute this operation until these two are done, right. I cannot do this operation until this is done. I cannot do this operation until this is done. So, this basically tell you the order in which you execute the operations, right. So, you can tell now, once you have this dependency, you can tell that I will do this operation in clock 1, this operation in clock 2, this operation in clock 3, and this operation in clock 4, right. So, this is what is called scheduling. Get my point? Any question? So, the tool actually does that, it identify the smaller operation, identify the dependency, based on the dependency it decide how many clock cycle I need to execute this behavior, right. This is what is called scheduling. So, this is done. So, once the scheduling is done, what I have to do? I have to decide how many multiplier I need, how many adder I need, how many register I need, right. So, basic intuition is what? The trivial way that how many multiplication operation is there, you use this many multiplier, but is it a good design? No, right. So, you have 1, 2, 3, 4, 5, 6 multipliers. Should I use 5 multipliers or can I use less? Can I use less multiplier for this? How? Any idea? When I can use the same multiplier to do more than one operation, right? Any idea from anybody that this is how I can use a multiplier to do 2 multiplication operation? Anyone? Some intuition should come, you should tell me. If this is my schedule, I am saying that this 4 operation is going to happen in clock 1, this 3 operation is going to happen in clock 2. So, can I do operation of clock 1 and clock 2 with the same multiplier? Right, right. So, that is the idea, sharing. Whenever whatever the multiplication happening here, they are working in parallel, right. So, you need basically 3 multiplier 1, 2 and 3, but once that clock is done, that multiplier is free. So, what I can do, I can take this multiplier and use, I can do this multiplication with the same multiplier, right. Similarly, this I can do with the same multiplier, right. So, this is how I can do the sharing. So, in this case I need how many multipliers? 3, because this is the maximum number of multiplier needed in one clock is 3. So, the tool exactly does that. So, it identify the parallel operations, and those are called non-compatible, right. So, they are basically working in parallel. So, they are conflicting operation, and 2 operations they are happening in 2 different clock, they are compatible. So, they can be done with this. So, you can actually map this problem in a graph coloring problem, and you can solve this problem and identify how many multipliers is needed, right. So, what about register? How many variables we have here? T1, T2, if you go back here. So, T1, T1, T2, you have basically T1, T2, this variable plus u dx and all, right. So, one trivial solution is that you use one register to store one value, right. That is the obvious solution. But again I will ask the same question, can I reduce the number of register? Similar concept, how? Yeah, so exactly. So, basically for a variable I have to see what is the lifetime of the variable, when it is defined, when it is last used, right. So, for example, T1 it is defined here, right, and it is used here. So, the lifetime of T1 is basically this. So, it's you need to store this value of T1 in only for S2 clock cycle, I do not need to store it anywhere else, right. So, now if two variables, say for example, now T5 it is lifetime is this. So, now you can use the same register to store both T1 and T5, because in clock 1 I will store T1 valued into this register, and in this S3 I will use the same register to store T5, understood. So, this is the decision that what is the minimum number of multiplier I need, what is the minimum number of register I need, what is the minimum number of adder I need, these are the decision, but this is a systematic algorithmic process, right. The tool can do these things automatically, and it is basically algorithm, right. You can identify the lifetime of the variable and you can do that, right. So, if you saw here I actually did that actually, this is the lifetime of T1, this is lifetime of T3 and this is lifetime of T3, T5, sorry T6. So, I can store this T1, T3 and T6 into the same register, right, because they have a non overlapping. So, this is how we can actually identify, understood. So, this is the decision is happening there. So, you first the tool identify what is the number of clock needed, then the schedule, based on the schedule they identify what is the number of multiplier needed, how many adder needed, how many register needed, understood. So, this happens for all operations, and then what you basically got here, that you basically identify that you need basically 3 multiplier, 1 adder, 1 comparator and few registers, right. So, that is the optimization. Okay. And then what happened, you have to these are the multiplier, these are the register, you have to make the connections, right. So, what you will do effectively, you know that in this clock 1 now this is the operation is happening. Okay. So, you have this multiplier 1. So, this is your multiplier 1, this is your R5, yeah. So, this is your R5 and this is your R7. So, you have to make a connection from R5 to this and R7 to this, right. This is the connection you have to do, and the output is going to R1, right. This is go back to R1, right. So, this way you read this operation and make the connections, right, is possible. This is in clock 1. Now, when you move to the clock 2, what will happen? Now, the same multiplier being used to compute this operation, right. Earlier R5 was coming, now R1 is coming, right. So, what you have to do? You have to multiplex the input, right. So, this is now earlier R5 was coming, now R1 is coming. So, I add this multiplier, right, and there is a control signal here which will be in first clock it will be 0, second clock it will be 1. So, that in the first clock R5 goes here, second clock R1 goes there, and so that in the first clock R5 into R7 happens, and similarly in the next clock R1 into R2 happens. Got the idea? So, this is how you can make the connections and you get your data path, right. So, this is the final data path for the design I have taken. Okay. And then these are the control signals, right, these are the control signals. So, this value will come from the controller, these are the control signals. So, you will tell that in the first clock you send here 0, so that R5 come here and R7 comes here and so on, right. So, the controller value will be determined by that way. So, these are the in controls S1, this will be your control signal, so that these 4 operation can execute in the data path, right. in S2 this will be your control signal, so that these 3 operations can execute in the data path, right. So, this is how your final structure will happen. This is your data path and this is your controller. The controller has this 4 state and this is the loop and this is your first block B1 and this is your B2, right. So, if you club these two, this and this, they will together will execute what? That for while loop that I have taken. You got the idea? So, this is what exactly happened in high level synthesis. This is not a magic, it does everything step by step. Any questions so far? Clear? Any question? I am going little bit faster because there are a lot of algorithms involved, but I just want to walk through with the process. So, this is the flow, and as I mentioned, within high level synthesis you have many optimization also. You can actually pipeline a loop, you can unroll a loop, you can partition an array, there are data flow, there are function pipeline, there are many optimizations that also you can apply, right. So, I am not showing what will be the impact, but you can do that, and that will give you different combinations. So, for example, pipeline give you latency optimized design with little bit more hardware, right. If you unroll, it will basically area will explode, but your latency will be minimum, right. So, these are all very well known studied thing. Okay. So, this you can also apply high level synthesis with, you just instruct the tool that you unroll this loop, pipeline this loop, it will do that for you. Okay. So far everything understood, right. So, now, but we are discussing ML accelerator. So, now what we want to do? I want to use this high level synthesis which will internally do all those things to give me a hardware, okay. And my objective is to use it efficiently. Okay. So, if you have a C++, so suppose you have a Python code, this is your ML model, right. Then you have a Python to C converter. So, that will give you C++, because this HLS tool will it basically does the from C++. Okay. So, this is how you can, starting from any machine learning model, you can generate the Verilog code, okay. And this is the HLS tool, and that will give you the RTL. Okay. So, that is the flow. So, you can actually use the tool, and if you download this Vivaldi HLS, which is basically free, you take any model, you can do this, you will get a Verilog code. Then you have basically hardware corresponding to the ML model. Now, the question is that we talked about that how LLM helps here, right. So, everybody know what is LLM, large language model, you are using, right, ChatGPT and DeepSeek, everything, right. So, the question that we are asking, in this flow, can LLM help you in developing the efficient hardware for the ML model quickly? Okay. So, let us see why we want to do it. So, now let us identify what is the manual effort in this process. So, this tool is automated, right, this HLS tool is automated, right, you do not need to do anything, you have to just give the input, it will automatically compile, although I have shown all the steps, but you do not need to do anything, you have to give a C code, it will give a Verilog code in a minute. So, then where is the manual efforts? I will talk about them now. Okay. So, whenever you convert this Python code into C++ code, that code may not be synthesizable, right. HLS tool may not able to synthesize it properly, because there are certain things which you cannot generate hardware for that. For example, recursive function, right, you do not know how many times the loop that function will execute. In hardware you cannot implement that, right, or say function pointer, dynamic memory allocation, malloc, calloc, because you have to develop a hardware where you say that my RAM size is 100. You cannot say ki when I run first time I will make my RAM size 100, next time 1 lakh, you cannot do it, right. You have to take a decision that in this design my RAM size will be 100 and I want to use only 100 size RAM. But dynamic memory allocation, malloc, calloc exactly does the opposite. You run the first time, you can use 100, next time 1 lakh, right. So, you have to those, if you have malloc and calloc, that has to be replaced with a fixed size, that you know that for your application that the maximum size will be say 40. So, I will decide my size of the array will be 40. Okay. Or if you have a function recursive function, you can always write in a for loop, right, iterative. So, those are called make it synthesizable thing. So, whenever you convert anything with a automatic converter, you will have malloc, calloc, you have recursive functions and all. So, somebody has to manually do this, replace all this malloc, calloc with this fixed static size, recursive function with this has to be done. Okay. Then if you look into this, as I mentioned that there are a lot of optimizations. You think about that your program has m line of code, okay, and there are n kind of such optimization possible. So, what is the number of possible way you can apply this optimization to this your code? M to the power n, right, because if there are m location, you can apply any of them here, right. If another location, you can apply any of them. So, it is m into m into m into n times, so m to the power n. So, these are the possibilities, right. So, somebody has to decide that I will apply this. So, that is not a easy process, but that is manual process here. HLS tool does not do that. If you do not ask him to do loop pipelining, it will not do loop pipelining, right. So, that is this part, that apply pragma based optimizations. The pragma is used to instruct the tool that you apply pipeline here. So, somebody has to do that hard task to apply the correct pragma, right. And also there are many source code optimizations are also there, which is basically I will talk about more, that whatever the C code, they may not be hardware friendly. Okay. You have to make the code hardware friendly. What is hardware friendly, by the way? Any idea what is hardware friendly? See, when you have say array access, right. So, when I write a code, I never thought about how many times I am reading the array elements. Probably I am reading the same array elements multiple times. Okay. But in hardware, whenever this map this array into say block RAM, every time you have to wait for one clock to get the value, right. So, if you read the value one value 5 times in your C program, you do not care, but if you read that same value 5 times, the same value 5 times, that means you waste 5 clock. Four of the clocks you could have saved, right. You read it once and store locally, right. So, that means I can rewrite my code such that I will not read any value from array multiple times, I will read only once, okay. And that version of the code is hardware friendly, because you are reducing the memory access, right. This is one of the example. So, that is what is called source code optimization. Again, these three is the manual effort. So, although it looks very good that you take your Python implementation, convert it into C, put it into HLS, it will give you the RTL, but these are the painful step you have to follow. Until you do it, you will not get your hardware. Okay. And specifically for say ML kind of model, where your line of code may be 10,000, 20,000, 50,000, this is not an easy job, right. It will take lot of time to make them synthesizable. Okay. So, this is where we are thinking LLM can assist, because LLM actually is a language model, right. So, if you tell him that you have this code and this is a recursive function, you convert into iterative function, probably if you have trained probably sufficient C programs, you will understand that, right, and it can do that. Or say you ask him to do the source code optimization, where you say you convert this loop into that. I will show you many examples. It actually can do very easily. You can check that it will do those kind of language processing thing very well. So, we leverage that facility of LLM into this flow, and this is basically LLM, right, and this is basically HLS. When I combine them, they actually make this process much easier, right, and that actually we have done, and we will show you some results how actually it is helping in developing good hardware from Python code or ML model quickly, okay. And we will show you that it is actually give you lot of optimizations. Okay. So, I will go through. So, I am not going to talk about what is large language model, everybody knows that, and it is being used everywhere. So, why not in this field also, right, I mean developing accelerator. So, and there are a lot of recent times interest in LLM, and there is a specific conference is happening nowadays, LLM aided design. How do you use LLM in your design flow, so that you can do the design quickly, okay? And almost everybody involves, all the big companies are involved there, and it has a conference this time in Stanford University, right. So, a lot of interest in the community to use the features of LLM in the VLSI design flow or the design flow, right. One recent research is happening where people saying that why I need HLS, I do not want HLS, I will say ki this is my C code, give me the Verilog. LLM understand this, right. So, why I need the HLS, I will replace HLS with LLM, right. There is a recent work is happening. So, where basically it is kind of a chat bot, right. There are quite few are like chat EDA, chat pattern, chat Nemo, where basically you give the specification maybe C code, and using this LLM and agent in loops, probably it will not give you correct Verilog at the first go. Then you tell that these are the mistake, and that mistake also you can identify, you will just running in your GCC, right, and you see this or say this some Verilog simulator, and you say okay, these are the syntax error. You identify, and that LLM again was prompted that you correct this mistake for me, right, and with multiple iteration it will correct and give you the Verilog, right. That is the kind of things are happening, and there are quite few such work, right. Verilog, that VeriGen, which is very recent work, then this is Verilog generator, right. So, you see here you have basically they just train the model with a lot of Verilog code, maybe all GitHub of Verilog, right. So, and then they train the model and then they try to do this, right. So, there are so many work. So, I am not going to detail of them. Then AI Verilog generation, then there are zero shot RTL code generation from specification using large language model. So, there are quite few interest in this domain. Now, the question is then do we need a HLS, right, that is the question. So, if LLM can give you the Verilog, then I do not need HLS, right, I do not need HLS, I just use LLM, right. So, is there any value of HLS, right. So, that study we try to do, and then we figure it out what is happening in this community, and this is the kind of design the current LLM can generate correctly, which is basically just simple 2 input multiplexer, 3 input priority encoder, half adder, FSM with 2 states, right, truth table of 8 bits and so on. So, these are very small design, right. So, although LLM can generate correct Verilog code, you do not need to write Verilog code, it will give you, but the design size is quite small, right. So, whereas if you consider the ML models, we have considered 6 ML model in our experiment, the code size is 4,000, 10,000, 1,48,000 and so on, right. This is the kind of model size, this many layers. So, it has basically 8 layers, first layer has 640 neurons, this has 18,460 neurons and so on, right. So, this is the size of your, these are also small model, these are not the big models, they are very small models. So, the size of your design is too big, and LLM is not something can adopt or handle such big specification and give you Verilog code, right. So, it is basically the takeaway of the discussion is that I do not want to replace HLS with LLM, rather LLM will improve the HLS based RTL code generation process, right. The way I talked about that you take those manual effort and use LLM there, okay. So, that will help. So, I will give you basically this will become now LLM. So, then this process is easy, you do not need to break your head there, right. So, it is basically LLM will make all these things done for you, and then HLS will give you the Verilog code. That is the viable approach, okay.
So, why LLM can design small designs, and what is the bottleneck here that it cannot design these large things?
Yeah. So, first of all, as we discuss in high level synthesis, a lot of decision is making is there, right. So, how many clocks is there, how many clock cycle you need to execute, how many register is needed, how many multiplier is needed. So, that decision LLM cannot take, right. It is basically a language converter, it try to do a one-to-one mapping of the instruction kind of. So, whenever those kind of complex decision has to be taken, and LLM is not aware of them, right, and it will just mixed up. So, That is why if you just see here, these designs are only very few lines of code, right, maybe 10-15 lines of code, right. So, it is not that efficient.
So, is it a question, so then it is a good path to take?
Which one?
So,
So, if you ask me, it is not a good path to take. So, because high level synthesis has lot of design decisions, and that is why I spent almost 10 minutes on scheduling, allocation, binding. I know that is little bit extra for me, but just to emphasize that high level synthesis is not just a trivial process, lot of decision is happening there, and unless you understand the decision, I mean so many decision steps, you will not appreciate that HLS is far better than LLM, right, in generating Verilog code from C. Understood? Okay. So, we have taken this and then we do this funny experiment, right. This is done by my students. So, what he did is effectively the first step that makes sure that synthesizability. So, we identify these are the primary issues when you generate a C code from Python, that you had dynamic memory usage, system calls pointer, function pointer, recursive function. So, what we do is basically we run it in high level synthesis and it will give you this, these are not supported, those error message we give it to LLM, right. So, we do not identify anything manually, we just give the code to HLS, it will say no, I will not able to handle your line number 50, line number 71, line number 32, because there is a malloc is there, there is a system call there. So, all these things will your HLS will give me, right. Then what we will do, there will be another LLM that will parse that and identify all this error and create the prompt and give it to LLM, and then based on that LLM will correct those things, right. It is a repetitive process, you cannot just get everything in one go, maybe 10-15 iterations, this will give you the code which is synthesizable, at least there is no such thing which is not supported by the HLS tool, right. This is what I have done and it actually does very well. You have to just give you some instruction earlier that if you this code you convert into this. So, you have to basically play with the LLM to tell him that the dynamic, if you have malloc you write the code into like this and so on, right. So, then he will understand. Then as I mentioned, these are the kind of examples. Say for example, if you have a dynamic memory allocation, then you replace with a static memory allocation. If you have a function pointer, you replace with a fixed pointer and so on, right. If you have a recursive function here, you convert into a for loop, right. So, this is LLM will do for you. Okay. Then LLM for source optimization, this is something I want to spend little bit of time. So, as I mentioned, what are the things, how to make your code hardware friendly, right. So, there are many source code optimization, one of them is loop merging. Say for example, you have four for loops here, right, 1 for loop, 2 for loops, 3 for loop and 4 for loops. So, you can do one, I can combine these two and I can write one for loop for this, right. This is what basically happening here. Then what will happen? This operation and this operation will happen within one loop. Then there is a possibility of parallelism, right. I can execute both of the operation parallelly, right. So, then if it take n clock cycle, it will take 2 n clock cycle, but if I do it parallelly, probably you can do everything in n clock cycle. So, this is what I am talking about, the hardware friendliness, right. Instead of having too many loops, you can merge similar kind of loops together, so that you can run the body of the code parallelly and it will improve your clock cycle, right. So, this is what one of the code optimization. So, again if you just give this prompt and you give this code and this is generated by LLM. So, it will basically identify and it will actually identify that you cannot merge this with this, there is a data dependency, okay, or you cannot merge this with this, at least this kind of things it identifies, only whatever mergeable it merges, right. This is exactly generated by LLM, not by us. Similarly, loop interchange is another thing. So, for example, you have everybody know matrix multiplication, right, everybody have written the matrix multiplication code, right. So, there are basically 3 for loop, right, I, j, k, right. So, if you have the first for loop is I, then second for loop is j, then third for loop is k, and effectively what happened, there are 2 matrix, right. You take one of the row, you take the column and then multiply element wise, right. So, this k actually go element wise and this basically this I select the row, this k select the column, right. And then this sorry, I select the row, j select the, this is your I, this is your j and k selects the elements, right. So, if you have this I j k and you just convert into k j I. So, you basically bring this loop here, only the order in which the operation getting executed will change, right. So, your final output will be same, but intermediate value may be different, right. But this k I j is much more hardware friendly, because the locality of reference is increased, right. You are not going to read one value or multiple, you are not going to read one value. In this you are going to read the same value 10 times, but here if you write k and j, k I j, you are going to read once and reuse more. You can do that, you can go and check detail, but that actually happen, right. So, just converting in your I j key into k I j make your code hardware friendly, right. So, that is called loop interchange, right. So, similarly you have loop tiling, this is another very interesting. So, the systolic array architecture Professor Mishra was talking about yesterday. So, here basically this is your that one box of module, right. So, effectively you have I j k, you are basically doing for entire thing, right. So, you are computing for entire thing. What you do, you create a tile of small tile, right, and this I j k is basically this tile. So, you compute. So, you are supposed to do something from this to this, right. So, now I will do the same thing only for this part of the code, part of the data, right. I will do the same thing for this part of the data and this part of the data, and this I can do parallelly. That is what is the systolic array architecture, you can take advantage of that. So, what is happening here, you have I j and k, you have still this I j k, but it has become 6 nested loop now. This is the one block, right. It is happening for say k k times, right, and now this loop will be incremented by tile size. So, you are basically you take this, perform this operation, then you go to this one and you perform the same thing, right. So, this is what is basically tiling, and this is actually is very important optimization for making your code parallelize, right. You can actually run this all module in parallel if you apply certain optimizations. So, these are the thing LLM can do you. If you just give this code and apply this, you give this instruction, it will give you this code. Okay. Similarly, as I mentioned, there are pragmas, pipeline, unroll and all. So, you can actually apply them. So, if you give this code and if you give this prompt, it will add pipeline here, unroll here, and this is actually a good decision, okay. Because if you unroll this, that means it will basically flatten, right. You need lot of areas, lot of units, and then you pipeline here. Whereas, if you unroll here, the entire thing will unroll, this 2 nested loop will unroll. So, you need basically n square area. Here earlier if you need one area, if you unroll the inner loop, it will need n area. If you unroll both of the loop, it will need n square area, right. So, what they are doing actually intelligently, that it actually unroll the innermost loop. So, that you need, instead of one area, now it is 1 unit of function unit, you need n unit of function unit, but then you pipeline the entire module, right. So, this is a good decision, and this is basically done by LLM with this prompt, right. So, this is the kind of design decisions. So, effectively this is our flow, which is we have given the name LHS, which is LLM assisted HLS, right. This is specifically for ML model. So, you have the CNN model, you have this keras to C, which can convert the either model into C code. So, this is the C code, and then I use the LLM to correct my synthesis error. So, I give the LLM to correct it, and then I do the HLS, and if there are some error, I go back and then correct it, right. So, if there are synthesis not successful, go back, identify what are the problem, give it to HLS and go back. So, after some loop, I will get the synthesizable code, right. And then I use this LLM to identify all these source code optimizations. Then I get the source of code optimized code, then I use LLM to insert the pragmas. I got some pragma inserted code, then I do the HLS. I get the RTL, I check whether this my target latency meet. If it is yes, done, otherwise you go back, get some prompt from here, and again instruct the LLM to do the thing, right. In some iteration, it will give you the efficient hardware, right. So, this is the kind of framework we have developed. So, I am quickly go through the results we have obtained. So, this is the kind of model that I have already talked about, and this is the FPGA board we have used. And here we have what we have tried is that I want to make I want to, first of all I want to fit this design into this board, right. If you can fit it there, I am done, that is my objective, right. And when I fit, I try to optimize the latency. So, I want to make sure that it is kind of resource constant latency optimization, that I want to make sure that this design must be fit into this FPGA board, and and then you optimize the latency for that. Okay. So, this is what happening, and this is the detail of the model which you can skip. We have used this Vivado HLS high level synthesis tool, ChatGPT 4 for the LLM. Okay. So, interestingly you see that the number of prompts are not high, right. So, for source code optimization we need only 4 or 5 prompts, right, but the same thing will applicable to many snippets, the same kind of code, right. So, this is the showing that number of prompts I am using, and interesting, the number of prompts are actually quite less. You can actually easily convert them into, so this is for source code modifications and all. So, it do not take much time to convert them into synthesizable code. Okay. And similarly, this is for optimization, right. So, it is basically for number of prompts, here the prompt is bit high from the first one. So, then in the first task of the making the code synthesizable, LLM is quite good doing that, because this is a very mechanical work, right, and LLM is going good in doing that, and this is the some results for that. And then what we did is basically so that the improvements, say for example, you see this is the design, the baseline latency was this much. So, this many clock cycle, you can see it is kind of some crore, right, this many cycle is needed to give the output if you do not apply any optimization. And then once we did this with say everything source code and pragma based optimization, this is the latency I got, and the improvement is 26 times, right. So, I am able to improve the latency by 26x. For the same next design, we are able to reduce the latency by 2690 times, right. If earlier it is 2690, it become 1 now. So, this is the kind of latency optimization we are able to achieve through LLM. We have not done anything, right. So, we have just used LLM to apply this pragmas, apply the source code optimizations, and this is the kind of improvement we are able to get through LLM, right. So, that is something interesting, right. So, LLM can help you. So, there is one more tool called HLS for ML that also does the similar stuff, that if you take a ML model, it will give you the Verilog code, and what we found that it was quite difficult to generate a Verilog which can fit in a target board, right. So, either it will optimize the latency and give you a design which has too much of area, it cannot fit into any board, or it will give you a design which has very less area, but the latency is too high that it cannot be useful, right. So, that is the problem with HLS for ML, and it is very difficult to play with that. There is an option called reuse factor, but that also very hard to apply. Okay. So, it is basically when we try to do that, we are able to see that at least for 2 design we will not able to do the synthesis at all, right. So, whatever pragma they are inserting, that HLS tool is not able to synthesize the thing. And among these 6 design, in 4 cases our this LHS work, which is LLM based optimization, actually beats HLS for ML, right, in terms of the overall performance, right. So, here you can see that our performance is, we are able to improve it is by 10,000, it is 6,000, right. So, it is 49 here, our case 52 and so on. Some cases they beat us, 2 cases, but this is an automated platform, right. We are not doing any optimizations on our hand, right. Everything is LLM is doing, right. We are only using LLM to optimize the design. So, so that is something is interesting, right. And in future actually some part of the things is still manual, in the sense we can this whenever there is a synthesis error, at this moment we just extract the error and give it to LLM, but that also can be done by another LLM agent, right. So, that is the enhancement we can do, then the entire process will be completely automated. So, this part is manual at this point, but which can be trivial extension. Okay. So, that is all for this session. So, in summary, LLM can actually be utilized in the HLS flow to create efficient ML accelerator, right, and it has been demonstrated with this work. Okay. So, thank you. So, we are done for this session. We will have half an hour break. We will come back after 30 minutes at 4. Okay.